Important points in relation to simulation are the following. Simulation is event-driven in that events trigger more events. Verilog modules contain processes which give rise to events that must be handled by the simulation. Some events are for the current time and others are for a later time. When the events for the current time are completed, the simulator then moves on to the next time containing events. The simulation timeline looks like this, with the simulator starting at time t is equal to 0. The simulator advances the simulation, and at time t, the events in the active queue are then processed for that time. Lots of events are handled by completing all the events in the active queue at this time t. And this is known as the simulation cycle. The simulation cycle is the time the simulator takes to complete all the events in the active event queue. We don't put an actual time value on the simulation cycle. The term simulation cycle is just a label for the time during which the simulation handles all the events in the active event queue. In practice, for large designs, it's possible that tens of thousands of events are dealt with during the simulation cycle. But from the simulation viewpoint, it has taken 0 time to complete. And this is how concurrency or parallelism is modeled in Verilog. There is one issue that we have to deal with, and that is the freedom with respect to the order in which the simulator selects events from the active event queue. And this is referred to as non-determinism in the simulator. We need to look in more detail at this aspect of the simulation to see if it is a problem. The Verilog reference manual makes reference to determinism and non-determinism, and the standard guarantees a certain scheduling order. In the case of the initial construct, we are guaranteed that this statement will complete before the statement that follows it, and so on. We are guaranteed that the statements are evaluated in the order listed inside a begin and end. And this is a form of determinism. There are two sources for non-determinism in Verilog. The first source is the order in which events are taken off the active event queue. And we've seen this, that the simulator has a choice as to which event to pick in the active event queue. The second form of non-determinism can be seen with the following example. Here we have two initial constructs. When the simulation starts, both are added as events to the active event queue. The first point to note is that the simulator can pick either initial construct to begin with. It's not a case that it always picks the first one listed. So it could actually start with this second construct here. Now, the second form of non-determinism states that statements without time control, so in other words, when we have no delay control, such blocks do not have to be executed as one event. And what this means is the following. Let's say the simulator starts with this initial construct, processes the first statement. Now, you might expect that after doing that, it'll proceed to the second statement and third statement in the order listed. Now, it is possible that the simulator could do this, but it's also possible that after the simulator executes the first statement inside this initial block, it then moves to this other initial block and executes the first statement in there. It then can come back to the second initial and complete the second statement in here and complete the third statement in here, and then back up to our first initial block and complete the second statement in here. So what we mean by interleaving is that it's possible for the simulator to move between the two initial blocks when processing these constructs in the active event queue, but we're still guaranteed that statements in a block are executed in the order listed. The problem with this in our example is that when the simulator executes this third statement, the value in A will always be 0. The value for B depends on whether this particular statement has occurred before we execute this statement for the update to C. When we perform the update to C, we know that this statement has occurred, but this statement here may or may not have occurred before we execute C. And if it has, the value for C will be 1, and if it hasn't, the value for C will be 2. And we've no guarantee as to which value will be assigned to C. Because the initial construct is not an atomic event, that is, other events may be interleaved with statements inside an initial, it is good practice to ensure that an assignment to a variable does not occur in different initial constructs. In the example shown here, we should only update B in one block. Note the code given here is for illustration purposes only and has no useful purpose. When we say that this avoids a write-write race, we mean that we are avoiding the situation when the order of writing a new value into B impacts the outcome.